It's easy to forget that there are these invisible rules that run pretty much everything around us. I'm talking about everything from a planet spinning around the sun to you just sitting there right now. There are these unseen pushes and pulls happening all the time. We call them forces, and they're kind of like the secret language of the universe. So how about we start learning how to speak it? Take a look at this. A simple bike ride, right? But if you could see the forces, you'd realize it's a constant battle. You've got the cyclists using their own muscle power, a force, to push the pedals. You've got the wind pushing back against them, another force. And when they coast downhill, some invisible force is pulling them, making them go faster and faster without even trying. And that pull? That's gravity. Every single moment is this little dance between all these different forces.
All right, here's a question for you, and we've all been there. Why is it so much easier to slip and fall on a wet floor than on a dry one? Seems like a simple question, but the answer gets to the heart of what one very specific force is all about. So just keep that question in the back of your mind. We're going to come back to it, and the answer is pretty cool.
So what are we really talking about here? In the world of physics, a force is basically just a word for a push or a pull. That's it. It's what happens when things interact with each other. And to measure just how strong that push or pull is, scientists use a unit called the Newton, named after the guy who basically wrote the rule book on this stuff, Isaac Newton. Okay, so a push or a pull sounds pretty basic. But what these simple actions can actually do? Well, that's where things get really powerful. They are the reason anything anywhere ever changes. Let's take a look at what they're capable of. Think about this fielder. That cricket ball is zipping through the air, moving fast. And then, bam, the force from the fielder's hand completely changes its motion, bringing it to a dead stop. This is one of the main jobs of a force, to change how something is moving. And forces don't just change an object's motion, they can change the object itself. When you stretch a rubber band, the force from your pull is literally rearranging its structure, deforming it. The object's actual shape can be changed by a force. So, let's just recap. Forces are the ultimate game changers. A force can get something moving from a total standstill, like kicking a soccer ball. It can change how fast something's going, speeding it up or slowing it down. It can change its direction, like a bat hitting a baseball. And like we just saw, it can even change an object's shape. Now here's where we can start to sort all this out. We can basically put every force in the universe into one of two big categories. First, you have contact forces. These are pretty straightforward. They require objects to actually touch. Then you've got the really mind-bending ones, non-contact forces. These are the forces that can work their magic across empty space. Let's start with the category we know best, the ones we can actually feel. The most obvious contact force for us is muscular force. Every single time you walk, lift something, or even just take a breath, your muscles are contracting and creating a force. And of course, it's not just us. Animals use this exact same force to do everything they do. It's basically the force of being alive. Okay, picture this. You roll a ball across the floor. You give it a push, a contact force, and off it goes. But after a little bit, it slows down and then it stops. You didn't touch it again. So what happened? What invisible force put on the brakes? The culprit is a contact force called friction. Friction is the resistance that just shows up whenever two surfaces try to slide past each other. And its one and only job is to oppose motion. You can think of it as the universe's built-in brake system. It's funny, we spend a lot of time trying to get rid of friction with things like oil, but without it, you couldn't walk, a car's tires wouldn't grip the road, you couldn't even hold a pen. And here is the secret to how friction works. If you zoom way in, you see that no surface is truly smooth. They all have these microscopic bumps and grooves. So when two surfaces slide, these little imperfections snag and lock into each other. And that is what causes friction. Which brings us back to our slippery floor. The water fills in those little gaps, making it harder for the surfaces to lock together. Less locking means less friction, and less friction means you're probably going to slip. All right, we've covered the forces that need to touch. Now let's get into the really wild stuff, the non-contact forces. These are the ones that seem to defy common sense, acting across empty space like real-world magic. So let's start with a classic experiment. You take two of those donut-shaped magnets. You slide one onto a stick, then you try to slide the second one on top, but you flip it over so that the same ends, like the North Pole and the North Pole, are facing each other. What do you think is going to happen? Whoa! It floats. The top magnet just hovers there in midair, held up by a completely invisible cushion of force that's pushing it away from the magnet below. This is a perfect example of a non-contact force doing its thing. It is pushing without touching at all.
What we're seeing here is, of course, magnetic force. It's that invisible field that surrounds magnets and gives them that incredible ability to either pull things closer or push them away, all from a distance.
Here's another bit of everyday magic you've probably done yourself. Just take a plastic ruler and rub it really fast against a sweater or even through your hair. What you're doing is building up a static charge. Now, take that ruler and bring it close to some little bits of paper.
And look at that. The paper literally jumps up and sticks to the ruler. Once again, the ruler is pulling on the paper without any physical contact. It's another powerful non-contact force in action.
This little phenomenon is called electrostatic force, and it's all about the push and pull between electric charges. The rule here is super simple, just like with magnets. Opposite charges attract, and similar charges push each other away. And finally, we arrive at the big one, the force that's keeping your feet planted on the ground and the moon circling the Earth, gravitational force. It's the pull that every single object with mass exerts on every other object. Here on our planet, we just call it gravity. And unlike magnets or static electricity, gravity is only ever attractive. It only pulls. It never, ever pushes.
Now, this constant pull of gravity leads to one of the most common points of confusion in all of science, the difference between mass and weight. They sound like they're the same thing, but they are totally different concepts. Let's clear this up once and for all.
Okay, here's the breakdown. Mass is the amount of stuff in an object, how many atoms it's made of, and that amount is constant. Your mass is the same whether you're on Earth, on the moon, or floating in deep space. Weight, on the other hand, isn't stuff at all. Weight is a force. It's the measurement of gravity's pull on your mass. And since the force of gravity is different in different places, your weight can change. So, let's finish with this little thought experiment. Imagine you have a 1 kilogram object. Here on Earth, its weight is about 10 newtons. But if you took that same object to the moon, it would feel super light, weighing only about 1.6 newtons. Take it to a giant planet like Jupiter, and it would feel incredibly heavy, weighing over 25 newtons. The whole time, the object's mass, the amount of stuff it was made of, never changed. But its relationship with the world, its experience of force, was completely different. It's a powerful reminder that all of us and everything around us are in a constant, invisible dance with the forces that shape our universe.